let's consider another little known property of aluminium. Aluminium is non-magnetic. In its normal state, aluminium is non-magnetic. So magnetism can pass through aluminium just like it does through paper. So aluminium will behave like paper in steel filings on the surface being manipulated by a magnet. In your schoolboy days, remember when you had iron filings on a sheet of paper and magnet underneath? Aluminium will behave exactly the same way. It's transparent to magnetism and not magnetic. When electricity flows through a conductor, it causes a magnetic field. So if aluminium is conducting electricity, it will be the electricity that creates the magnetic fields. Another important little understood property of aluminium is its thermal conductivity. Again, aluminium has 57% the thermal conductivity of copper on a volume basis. So if you've got a bar of aluminium 10 millimeters diameter and a bar of copper 10 millimeters diameter, aluminium would be able to conduct 50% the conductivity of copper. But on a weight basis, so if we match the weight of the copper with the weight of aluminium, the conductivity of aluminium is 200% that of copper. Now we can start combining the properties of high thermal conductivity and low weight. So aluminium is absolutely optimal for heat exchangers, for car radiators, cooking utensils, and engine cylinder heads. Aluminium dominates air conditioning, and it's extensively used in cooking pots and pans. So no muscle-bound cooks. Can you imagine how many people Michelin star chefs would have killed with flying copper pans? If we apply the high thermal conductivity of aluminium to heat sinks, we can apply the high thermal conductivity of aluminium to heat sinks. Now, heat sinks are attached to electrical chips inside your computer, inside your phone, inside your television or microwave. There are heat chips, very semiconductor devices which switch, modify the electrical power through them. Now, those semiconductor devices work at extremely high current density levels that they would melt. But by attaching aluminium heat sinks, thin devices to dissipate the heat to them, the aluminium keeps those chips cool and allows them to work at high current densities. So without aluminium heat sinks, semiconductors will melt. And without aluminium lightweight heat sinks, iPhones, laptops, televisions, microwaves would not be possible. So the high thermal conductivity of aluminium enables your laptop, your chips to work. Aluminium has one of the lowest melting temperatures of all metals. Only magnesium has a slightly lower melting temperature. Pure aluminium melts at 660 degrees C. Some aluminium alloys melt at temperatures low at 550 degrees C. So aluminium melts at just around red heat. It melts at an extremely low temperature. Steel melts at 1500 degrees C, copper at 1000. So aluminium has an extremely low melting temperature of most metals. Now, the low melting temperature makes aluminium optimal for castings because the molds, the melting furnaces are simple. We don't need to use highly alloyed steels for the molds, for the dies, for the furnaces. Because it has a low melting temperature, molten aluminium is easy to handle. It doesn't have high radiation. It's not spitting and spatting, and it's not blinding you. Now, the low melting temperatures mean low minimal energy losses through convection and heating. So if we melt aluminium and we've got it in a crucible, we're not losing heat to the atmosphere. And that means that we can have simple heating, simple installation to result in low energy losses. Now, aluminium is a light metal, and in its molten state, particularly its silicon alloys, it exhibits extremely high fluidity, approaching that of water. What I mean is that when you melt water, particularly the 4000 series silicon alloys, they literally flow and behave as water. Now that means that aluminium is absolutely optimal for castings, for casting fine details. If water can flow in, aluminium can flow into your fine details. Absolutely perfect for castings. Now, in the United Kingdom, about 40% of all aluminium used goes into castings. And remember that aluminium has 40% the melting temperature of steel, and that casting is liquid metal engineering. So aluminium is absolutely suited for casting. And it's used to produce engine blocks, cylinder heads. Let's look at the low temperature performance of aluminium. Now, aluminium alloys have no ductile to brittle transition. Some steels, as they get cold below room temperature, become brittle and fracture. There's a great hypothesis that the Titanic sank because the steel used in the Titanic was brittle at about 4 degrees centigrade, the water temperature. Now, aluminium does not have a ductile to brittle transition temperature. Now, as the aluminium atoms contract, their metallic bond attraction increases. So as aluminium gets colder, it gets stronger. So the yield and tensile strengths of aluminium actually significantly increase with decrease in temperature. And the ductility of aluminium actually slightly increases with decrease in temperature. So aluminium has no brittle transition temperature at low, or is not brittle at low temperatures. So, and aluminium alloys actually increase in strength and ductility with increasing temperature, decrease in temperatures, do apologize. So it's extensively used in cryogenic applications. Now, those are the liquefaction, transportation, and storage of liquid gases. Remember, it does not get brittle at low temperatures. So aluminium is used in applications as gas bottles for gas production, transportation in hospitals and ventilators. We've looked at low temperature. Let's look at high temperature. And at elevated temperatures, remember aluminium has a low melting temperature. So when metals are heated, they expand and as they expand, their metallic bond is weakened. So at temperatures up to about 100 degrees C, the mechanical properties of most aluminium alloys and tempers are not affected. But remember that aluminium has a low melting point. Pure aluminium melts at about 660 degrees C. Some of its alloys melt at as low as 550 degrees. So elevated, get low temperatures, I say elevated temperatures, so at 3, 4, 500 degrees C, which are elevated temperatures, but low temperatures when you're thinking in terms of steel, the yield and tensile strength of aluminium rapidly reduces. Aluminium also becomes superductile. So the strength of aluminium falls off very rapidly at low temperatures, 3 to 4 to 500 degrees C. Now remember, we can't exist at temperatures above 60, 70 degrees C. And cars are designed for a maximum working of a temperature of 110 degrees C. So although aluminium at relatively low temperatures, 3, 4, 500 degrees C, loses its strength, it's not a problem for most applications of aluminium. So at 200 degrees C, relatively low temperature, aluminium has got about 80% of its yield strength. So at 200 degrees C, aluminium's about 80% of its room temperature strength. By the time you get to 300 degrees C, it's at a third, 30% of its yield strength. Now, this is such an important property because it enables aluminium to be hot formed, hot rolled, particularly extruded and forged using low forces at relatively low hot working temperatures. You would hot work aluminium at 300, 400 degrees C. You hot work steel at 1200 degrees C. Very, very important property of aluminium. The fact that it loses strength at relatively low elevated temperatures.